Hello, I was wondering if there was another way that we could test the distance to the moon, and I came up with this idea. Let's just pretend for a minute that the Earth is round and it's not flat. If this circle that you see is the equator, so we're looking at the Earth from, let's say, the North Pole or the South Pole, if the moon is directly above this point along the equator, somebody who's on this side won't see the moon perfectly parallel relative to this observer, and this observer on this side won't see the moon perfectly parallel as well. So in essence, if the Earth is this way, there's going to be an angle difference, A, that is going to be an angle deviation from true parallel. And so if you have the observer in the middle looking at the moon directly straight up, and you have somebody over here on this side of the world looking at the moon at the same time along the equator, so both observers would have to be on the equator, and the moon would have to be directly over the equator at the same time. Then if you can take a proper measurement of the moon's elevation with enough precision, you could theoretically calculate the distance to the moon. So we have 360 degrees of longitude around the Earth like this, and we have well-established latitude, longitude coordinates for every location on Earth, so it's not going to be that hard to get an exact geo-coordinate for 2 points on the Earth. If you have one observer at the ground position of the moon's current location, and at the same time you have somebody else over here with a known longitude difference, if we know what the radius of the Earth is at that point, we can calculate the distance that is perpendicular to the moon's light rays that hit the surface of the Earth at its GP. And of course, if the moon is not an infinite distance away, then there's going to be an angle here, just like this, where the moon is a certain distance away. And that's going to form an angle A that we see here. So I used two different online tools to get latitude and longitude readings for various locations, and I chose March 18th, which is just going to be a few days away because the moon happens to be crossing the equator at that point. I transferred the readings over to this tab in a spreadsheet that I created, and I'm going to leave a link to the spreadsheet in the description below so you can look at it and look at all of the math that I've done. And if I made any mistakes, please let me know and I will gladly correct it and possibly make a follow-up video. So I have 3 locations. I've got somewhere in Congo, I've got somewhere in Brazil, and I've got somewhere in Malaysia. Actually, right about there. Those were the geo-coordinates. These were the local times because Mooncalc deals in local time. And those were the altitude azimuth readings that Mooncalc provided. So you can see that right here in the Congo, it was almost perfectly straight up with an azimuth of 342. This one was almost due east with an altitude of 8.26. This one was almost due west with an altitude of 9.14. If I come back over to here, what I'm trying to do is I'm trying to get this angle here. So the difference in longitude between Congo and Brazil happens to be the longitude of the one minus the longitude of the other. This only works on the equator. I wanted to calculate the x component and the y component, which would be the x over here and the y like this. And so you can see that the difference between Congo and Malaysia is positive x, and the difference between Congo and Brazil is negative x. I'm not really using the y. I was thinking of using that for something else. I might rework this spreadsheet before I make it available. So now the next thing was I wanted to calculate the difference in the angle. And this is the difference in the observed angles between this one and this one. And so at this point, because the moon has just passed the GP of the Congo, and I couldn't be bothered to fix the time so that it was directly above, this observation was facing west, this one was facing east, so I had to create some sort of alternate altitude So both observers were facing in the same direction. And so this one is 180 degrees minus this altitude. And so this difference between these two angles is the one observed altitude minus the other observed altitude. And if this one is at a 0 degree reference direction, for lack of a better word for it, I want this one to be normalized to this one. So what I ended up doing was taking the observed altitude and subtracting that from the angle to the expected tangent line, and that was done by subtracting this theoretical zenith angle from 90 degrees. So according to my calculations, that gave me an angle of 0.8259 degrees, which should be this angle A. If we can estimate this length from this observer to the GP of the moon along the one dimension, along the x-axis, and here I just noticed I just corrected it. We know this angle A, we know this distance B, and if we want to know this length from the observer to the moon, we divide this side by the sine of this angle, and I had calculated 441,995 kilometers. And so I did something similar for the Congo to Malaysia, and I had worked out this angle A was 0.86 degrees and worked out this estimated distance here. I also did a third calculation, which was the distance between Brazil and Malaysia. And so what I did there was I just added these two distances to get this one, with the exception that there's an angle on this side plus an angle on this side. So the main difference here was that I had to divide that angle by 2 before continuing my calculations, and then I got 433,000 kilometers. And so I just decided to take the average of all three, and assuming that we had instruments capable of measuring an angle to 2 decimal places and a little bit of math, a radius of 6,371 kilometers gives us the distance to the moon of 433,000, when in reality, according to Mooncalc, at that time, the moon was 378,316 kilometers away. I wanted to verify that Stellarium was equally accurate and could produce similar results as Mooncalc. So this time I switched over to Stellarium and I chose 3 similar geolocations. They're not exactly the same. You can see this one's 19.304. This one was 20.45. Stellarium uses your computer's local time, not the observer's local time. So all of these are expressed in my local time. And I had to do a slight conversion of their altitude and azimuth that is expressed in degrees, minutes, and seconds, and turn those into a real number like this. And so now I have 3 locations, 3 measurements, and I performed similar calculations as before, and I got 428,065 kilometers as opposed to 378,000. And this works like this because the moon happens to be over the equator and the 3 observers happen to be more or less along the equator. But what happens if you're not on the equator? Can you do something similar for any location on Earth? So then I created a few more examples. In this tab, I chose 3 different geolocations. This is the same time in all 3. These are all my local time. I've got the reported altitude and azimuth as provided by Stellarium. And in order to be able to use any location on Earth, I have to normalize and rotate and transform all of the altitudes and azimuths into a common reference frame. And so the way I ended up doing that was, first I transformed the azimuth into a Cartesian coordinate system friendly angle. So wherever you are, an azimuth of 0 is due north, 90 degrees is due east, And if I want to transform that into a Cartesian coordinate system, due east has to be 0 degrees and due north has to be 90. I subtracted the azimuth from 90 degrees, and that gave me, in this case, an angle of minus 170 degrees, which is down over here in this direction over here. If the observer is the origin and the moon is on a shell around the observer with a radius of 1, what I want to do is I want to calculate that three-dimensional coordinate where the moon would happen to be. And so I just used sines and cosines like this in order to get an XYZ coordinate. Then if east-west is the x-axis, so here you can see the transformed x is just a copy of the x, but I want to rotate the y and the z-axis around the observer in order to compensate for the observer's latitude. I'm transforming that 3D coordinate around the observer's latitude, and then what I'm doing is I'm calculating a new altitude and azimuth. And so now I've essentially converted a local altitude and azimuth to an altitude and azimuth that should be equivalent if the observer was directly over the equator. So here I'm doing the same kind of transform for the other two observations. And now what I'm interested in is the rotation along the y-axis. So let's say the y-axis is parallel to either the north or the south pole. Then what I'm interested in is the difference in the angle between the two observers along that axis. I calculated the difference in the two observers' longitudes by subtracting the one from the other. I calculated the difference in the angle between the two, and the calculations are very similar. So in this case, the angle offset is the difference between these two angle deltas. And finally, the estimated distance is the same kind of calculation that I did before. So the main goal here was to calculate that angle offset A. That was the angle that I'm interested in. And from there, with a known radius of 6,371 kilometers, I was able to estimate the distance to the Earth. Calculated for one, calculated for the second, and calculated for the third. And finally, I averaged all three, and I got an average of 370,630, which is pretty close to the distance given here at 375,000 kilometers. If you pay attention to these three coordinates, they are going to be slightly different than these three coordinates here. And in this tab here, I just rearranged a few things around and made it easier for myself to replicate different observations. And I wasn't satisfied with just three. In this tab, I decided to try 5 different locations. And I also moved the transformation down underneath the other one so that I could see what all of these angle differences were at the top. And here's the average over here. And seeing how relatively successful that was, I thought I would apply the same process to the sun. So according to Stellarium, on June 15th of this year, the distance to the sun is going to be 1.02 AUs. In this case, I added a few extra calculations. This is a copy-paste of what is provided by Stellarium, and then I let the computer calculate and transform these values into altitudes and azimuths as expressed by real numbers. The transformation process is the same. The angle offset is the same kind of calculation as before. And now this simple process has told me that the sun is much further away than the moon. In this case, I am dealing with loss of precision, and as a result, the error is much bigger than it is for the moon. It's more like 145 or 147 million kilometers or something like that. It's not 3.4 million, but this process does show that if we can get accurate readings with the technology that we have, this is yet another confirmation that we live on a spherical Earth and that the sun and the moon are very far away from us. So I thought you would find that interesting. If you did, go ahead and leave comments below. give it a thumbs up, the subscribe, and all of that other good stuff that you know what to do. And I'm going to see you again in another video at some point soon enough. So bye for now.